Ever wonder how scientists untangle the messy web of cause and effect in real-world data? Like, how do they know if a new drug actually works, or if a gene's activity is driving a disease, instead of just being a side effect? Today, we're diving into a breakthrough in causal discovery, a method that mathematically proves it can find the real relationships behind the noise. Let's break it down. Imagine you're trying to map out a complex system, like how diet, exercise, and genes interact to affect your health. But here's the problem: data is messy. There's noise, hidden factors, and sometimes variables that look connected, but aren't actually related. How do you separate the signal from the static? That's where causal graphs come in, visual maps showing which factors influence others. But how do you know your map is right? The key here is a mathematical proof. Researchers showed that under specific conditions, like when the model is powerful enough to capture real-world patterns, their method can uniquely identify the true causal structure. Think of it like solving a puzzle. Even if there are red herrings or missing pieces, the correct solution stands out. How does this work? Let's talk about score functions. These are like fitness tests for graphs. The true causal graph gets the highest score because it fits the data best. Any wrong graph, it'll always score lower. It's not just guesswork, it's a mathematically guaranteed win for the right answer. But here's the twist: some graphs look different but behave the same under experiments. That's where Markov equivalence comes in. It's like different road maps of the same city, different layouts, but the same key connections. The proof shows that if a graph isn't part of this equivalence class, it can't match the data's patterns. Tools like discriminating paths help spot the differences, like finding a unique landmark that only exists on the real map. Now let's get practical. How do you test this? The team used fake data generated with a random network model called Erdős-Rényi, simulating variables like genes or economic factors. They tweaked things like noise levels and hidden confounders to see if the method could still find the true links. They even added nonlinear relationships, think of it as curves instead of straight lines, to mimic real-world complexity. To handle the math, they used a clever trick called the Hutchinson trace estimator. Instead of crunching impossible numbers, they sampled randomly, like estimating a mountain's weight by weighing a few rocks. Then they fine-tuned the model using Lasso optimization, which prefers simpler, cleaner graphs, like editing a messy photo to highlight the main subject. But this isn't just about theory. Let's talk about DCCD-CONF, the framework developed at Georgia Tech. Traditional causal discovery tools struggle with two big challenges: nonlinear cycles, like predator-prey relationships, and hidden confounders, third variables that distort apparent connections. DCCD-CONF tackles both by leveraging interventional data, experimenting with systems to observe ripple effects. Here's how it works. First, it guesses the causal graph structure, then iteratively hunts for hidden variables by adjusting the model to fit the data. It's like solving a mystery by alternating between what's the suspect's motive and who's been hiding in the shadows. This back-and-forth process lets it handle cycles and hidden factors without getting stuck. The results: DCCD-CONF outperforms older methods in two key ways. It's better at recovering true causal structures and identifying hidden variables. Tested on synthetic data and real-world gene datasets, it proves both accuracy and scalability. Plus, its mathematical foundation ensures reliability, no guesswork. Why does this matter? Imagine studying a gene network where feedback loops and hidden factors are the norm. Traditional tools might miss critical connections, but DCCD-CONF could reveal them. This isn't just a technical win, it's a leap toward understanding systems in biology, economics, and beyond. So next time you hear about causal discovery, remember, it's not just about what happens, but why. And tools like DCCD-CONF are helping us ask better questions. Stay curious.